Welcome to Mastering Operator Overloading in Python. We'll explore custom magic methods and dunder methods, essential for experienced developers. This session will enhance your understanding of Python's operator system, enabling you to implement custom behaviors and design maintainable code. Magic methods, or dunder methods, are Python's protocol for operator overloading. They allow custom classes to interact with Python's operators, creating intuitive application programming interfaces. For instance, a plus B calls A, add, B. This mechanism lets you define responses to operators like plus and indexing with. Magic methods, or dunder methods, are Python's protocol for operator overloading, allowing custom classes to interact with built-in operators. They enable intuitive APIs by transforming objects into first-class citizens. For instance, a plus B calls A, add, B, defining how instances respond to operators like plus and indexing with. In Python, the bot add bot method in a class like vector allows for intuitive addition of objects. When v1 plus v2 is executed, v1.add v2 is called, returning a new vector instance. This approach maintains immutability, a key principle in mathematical operations, ensuring that original objects remain unchanged while new results are produced. Arithmetic magic methods enhance class functionality. Add and nobby rad handle addition, with hobby rad managing right-side operations. Sub and nobby rsub are crucial for subtraction. Mul and nobby rmul support scalar and vector multiplication. Division is managed by hi-char trueDiv and floorDev, while hi-pow and hi-mod facilitate exponentiation and modulo operations, essential for scientific and cyclic computations. The money class exemplifies robust numeric operations with currency handling. It supports addition and subtraction, ensuring currency consistency, and allows multiplication by scalars. If an operation isn't supported, it returns not implemented, enabling Python to attempt alternative methods. This design ensures flexibility and reliability in financial computations. Understanding not implemented is crucial for robust class design. When a magic method returns not implemented, Python attempts the reflected operation on the right operand. If both fail, a type error is raised. This mechanism allows operations like 5-vector to succeed by trying vector. Armola 5. Avoid raising not implemented error. Always return not implemented instead. EQRS defines behavior for RRI, essential for custom equality. Na is usually derived from RRI. RRI is crucial for sorting, while RRI can be derived from RRI, and RRI is often reflected from RRI, and RRI is derived from RRI and RRI if available. The total ordering decorator simplifies comparison logic by generating missing methods from Baikshak EQY and Dakshak LTIs. In the task class, priority determines order, with lower numbers indicating higher priority. This allows tasks like code review, bug fix, and refactor to be sorted efficiently by priority, demonstrating the power of smart comparison implementation. Container magic methods enhance custom collections. Getitem and setitem allow bracket notation for accessing and setting items. Deletem supports item deletion. Len enables len obj functionality. Contains implements membership testing. Iter makes objects iterable, while I reversed supports backward iteration. These methods are crucial for creating efficient, flexible container types. The unique list class ensures only unique items are stored, leveraging magic methods for collection behavior. Len and syshan returns the list length, while nswitch getitem and sych and nsych setitem and switch manage item access and assignment. Contains checks membership, and nsy iter nsig allows iteration. The append method adds items only if they're not already present, maintaining uniqueness. The Pancham getitem RA method in Python allows advanced indexing, supporting both slicing and multidimensional access. In a time series class, slicing is handled by checking if the key is a slice object, enabling operations like obj one-sao. For matrix-like structures, getItem y can accept tuples, allowing multidimensional indexing, such as obj j, similar to NumPy. String representation methods enhance object readability and debugging. YANwrapper provides a developer-focused, unambiguous output, often used in debuggers. StarQuar offers a user-friendly view utilized by Print and Str. Format allows custom formatting, supporting f-strings and format with specifications like polar. These methods ensure clarity and flexibility in object representation. Context managers using achas enter, achas, and achar exit ach streamline resource management with the with statement. Dach enter ach sets up resources, while dachar exit acha ensures cleanup even during exceptions. For instance, database connection manages database connections, automatically closing them post-usage. Use contextlib.contextmanager for simpler implementations. This guarantees efficient resource handling, crucial for robust applications. Implementing call allows objects to be used like functions, maintaining state or implementing complex logic. For instance, a counter class can increment a count each time it's called. Similarly, a multiplier class can multiply input by a factor, creating flexible, reusable function-like objects. This is ideal for callbacks, event handlers, and the strategy pattern. getAttrBys is triggered when an attribute isn't found, allowing dynamic creation or lazy loading. getAttribute handles every attribute access, requiring careful use to avoid recursion. setAttrBy intercepts assignments, useful for validation or logging, while delatorBy manages attribute deletion, enabling cleanup or preventing critical deletions. These methods enhance control over attribute management. Dynamic config class demonstrates dynamic attribute handling. It uses shakshari getAttar shakshris to provide default values when settings are missing, and shakshri setAttar jakshris to validate and store settings. Shakshri getAttribute prioritizes user-defined settings over defaults, ensuring flexibility and robustness in configuration management. This approach allows seamless integration of dynamic defaults and user settings. In-place operators like +ka and ha use magic methods such as ba I add, thigh, and ba I sub I to modify objects directly. These methods should return self, allowing method chaining. For example, in a counter class, I add I and I sub I adjust the value attribute in place, crucial for mutable objects. Immutable objects typically don't implement these operators. Unary operators like neg I pos I, and abs I are crucial for numeric types, allowing operations like negation, positive affirmation, and absolute value. Type conversion methods such as int I float I, and by complex facilitate integration with Python's numeric tower. The Bartbol-Chawas method defines truth value testing, while Oz hash Oz ensures objects are hashable, crucial for sets and dictionary keys. Operator overloading should align with user expectations. If plus combines, should separate. Ensure logical consistency. Implement hash with eq-wadimes, and consider rad with add. Immutable types should return new objects, while mutable types modify in place. Use not implemented for unsupported operations and document behaviors clearly, especially for complex implementations. Avoid breaking commutativity. Ensure a plus b equals b plus a by implementing reflected operators. Never modify immutable objects in arithmetic operations. Return new instances instead. Prevent infinite recursion in Docker getAttribute by using object, getAttribute, or super. In-place operations, always return self. Implement hash when defining EQQ to maintain object hashability. The money class exemplifies proper operator overloading in Python. It supports arithmetic operations like addition, subtraction, multiplication, and division, ensuring currency consistency. Comparison operators are implemented for equality and less than checks, with a custom hash function for immutability. String representations enhance readability, while utility methods validate currency compatibility, ensuring robust financial calculations. Optimizing magic methods is crucial for performance. Avoid costly operations in frequently used methods like yaoi EQY or naoi hash. Naoi. Cache expensive properties, use naoi slots to reduce memory usage, and prefer built-in types. Implement lazy evaluation to defer computations. Use cProfile to identify bottlenecks. In optimized vector, jar slots, and cached magnitude enhance efficiency. Testing magic methods ensures robust operator overloading. For addition, verify same currency operations and handle exceptions for different currencies. Multiplication should be commutative, while equality and hashing must maintain consistency. Test comparison ordering to ensure correct sorting behavior. These tests validate the integrity and reliability of your class implementations, ensuring they behave as expected in various scenarios. Magic methods create intuitive Pythonic APIs by enabling operator overloading. Adhering to conventions ensures predictable behavior, enhancing usability. Return not implemented for unsupported operations to leverage Python's fallback. Prioritize immutability and thread safety by returning new instances for immutable types. Thorough testing and profiling are crucial for maintaining consistency and optimizing performance.